This video is going to be on some thermochemistry from your notes. It will be on questions 4 and 5 in your notes on page 3 and 4. The first part of this is on the online site, but it's a PowerPoint from this chapter. And there's a property called enthalpy, okay, and you're going to use this pretty much most of the year. And enthalpy is the heat flow between reactants and products in a reaction. So if you burn a match, the heat flow would be the energy is going from the substance to the surroundings. Okay, it's a very exothermic reaction. Enthalpy is symbolized with the letter H. Okay, it's very similar to the letter Q. Okay, H and Q are basically just the heat flow in a reaction or some kind of process there. You would typically use a calorimeter. Okay, use a calorimeter to figure it out. So you'd use a bomb calorimeter, do a reaction in there. So if you're doing the combustion of gasoline, you put some gasoline in, you measure out, okay, 1 gram of gasoline will produce how many kilojoules of heat. Okay, or if a reaction is endothermic, how many kilojoules of heat must be absorbed from the surroundings of this reaction. So the enthalpy is the H in the reaction, and we usually symbolize it by delta H. Again, delta H would mean the change in the reaction, so from products to reactants. If we subtract the products minus reactants, which has more enthalpy, which has more energy? If there is a decrease in energy, that means if there's less energy here, then delta H becomes negative. So if delta H is less than 0, if it's negative, delta H is greater than 0, it's endothermic. We're putting heat into the reaction. We're increasing in energy from reactants to products. If delta H is negative, it's exothermic. Okay, just same thing as Q. Same thing as Q. Again, one thing that's important, it's at a constant pressure as the reaction goes. Again, if the reactants have more enthalpy or more energy than the products, it is an exothermic reaction. So that means energy is being released. And the difference in energy between the reactants and products is how much energy, how many kilojoules of energy being released to the surroundings. If you have to add energy in from reactants to products, the amount of energy gained is your enthalpy change. And that would be a positive or endothermic reaction. Here's a thermochemical equation. Okay, thermochemical equation. So, same thing as normal chemical equation. It does tell you if a substance is a solid, if it's solid, liquid, or gas, or if it's aqueous. Okay, in every substance, solids versus liquids have different amounts of enthalpy. Okay, we'll get to that a little bit later. So the delta H for this reaction is positive 28.1 kilojoules. This is the important part, which you're going to use a lot. What that means is this. To make this substance go from a solid to dissolve, basically we're dissolving it in water here, to make it split apart into its ions, you must add energy. So if it was in water, it's taking energy away from the water. So you'd feel the water getting colder as this substance absorbs energy. It's an endothermic reaction. And it takes 28.1 kilojoules per mole of this substance. There's an important part. This is kilojoules. It's per mole of this substance. Or whatever number's out front of here. It's a 1 in this case. So 28.1 kilojoules per mole of this is absorbed to make it dissolve. Here's an exothermic. It is an exothermic reaction. I don't like that one very well. So I'm going to go back to your notes now. And here's number 4, thermochemical equations. Again, we'll worry about moles of gas another time, but it's basically everything I just told you there. Okay, if you have a thermochemical equation, so let's look at an equation. Your first rule of thermochemistry is, and there's 3 rules, the magnitude, in other words, the size of delta H, the size of the enthalpy change, is directly proportional to the amount of reactant or product. Obviously, the more reactant you have, the more gasoline you have, the more heat that is produced. So there's a stoichiometric ratio between those things. So we have an equation here. I apologize, the equation is written a little bit weird. Actually, let's rewrite the equation right now. So the equation is for every 2 moles of vanadium as a solid plus 5/2 moles of oxygen as a gas produces 1 mole of V2O5 as a solid. And the delta H is right here. And there's your delta H, your enthalpy change. Notice that you have a 5/2 of mole. The reason is they were trying to keep this as 1. So trying to figure out, this is the enthalpy change to produce 1 mole of this compound. So to do that, they had to make this a 5/2 mole. Otherwise, everything would have been 4, 5, and 2, had they written it otherwise. So here's the important thing to know about this. This much heat is released per mole of this. It's exothermic. Okay, as this reaction goes, that much heat is being released to the surroundings because it's a negative value. That much heat, that many kilojoules of heat are released per 5/2 moles of oxygen, or per 2.5 moles of oxygen, and that much heat is released for every 2 moles of vanadium. Okay, so it's related to the coefficients in here. So if 1 gram of oxygen reacts, what is the enthalpy of the reaction? So in other words, how much heat is released if we only use 1 gram of oxygen? So we start with 1 gram of oxygen here. Pretty normal stoichiometry, really. Oxygen would be 32 grams per mole of oxygen. Now we're going to use this ratio. I'm going to say that for every 5/2 mole of oxygen, for every 2.5 moles, for every 5/2 moles of oxygen, there's 1,579 kilojoules of heat released. For every 5/2 moles of oxygen, there's that much heat released in this reaction. And I'm going to be left with kilojoules. My moles cancel, grams cancel, be left with kilojoules. And you get about 19.74 kilojoules of heat. That would be how much heat is released. That's how much is given off. Notice it's much smaller than that because 1 gram is way less than 2.5 moles for that. Next question on here says if you had 5,000 kilojoules of energy was released in the reaction, so more than that, how many grams of vanadium must have reacted? So now we start with our 5,000 kilojoules. Again, I know I need kilojoules down here, so I'm going to use my delta H, my enthalpy change for the reaction, and say that, well, there's 1,579.14 kilojoules of heat released for every 2 moles of vanadium. That much heat for every 2 moles. Or I could divide it in half. There's half that much for every 1 mole. And then I can say that every mole of vanadium is about 50.94 grams. So I was trying to get how many grams. The answer there is about 322 grams of vanadium. So if 5,000 kilojoules of energy was given off, that's how many grams of vanadium reacted to produce that much heat. Again, that's an exothermic reaction in that case. So stoichiometry is pretty similar, just using the enthalpy change that's on there with it. That was question 5 in your notes. Here's kind of a follow-up to it. This would be on page 4 of your notes. I'm saying here that the relationship between delta H, the enthalpy change, and the amount of substance used for both chemical reactions and phase changes, like melting a piece of ice, okay, making water turn into steam. There's a certain amount of energy required for those things to happen. So using coffee cup calculators found that when an ice cube weighing 28.9 grams melts, it absorbs this many kilojoules of heat. Figure out delta H for the thermochemical equation. So notice our equation is just water to water, but solid to liquid. That would be an endothermic reaction. You have to add heat. We got to put heat into solid ice to make it turn into liquid. Okay, and the delta H for this reaction, actually we don't know the delta H. We're trying to figure out what it is. So we're trying to figure out how many kilojoules per mole does it take. We know that there's this many kilojoules for that many grams. So we want to know how many kilojoules per mole. So I'm going to say that for every 1 mole, if we had 1 mole of water, we could say that a mole is 18 grams of water. And then I can say that this many grams produce that, or takes that much heat to make it melt. So for every 28.9 grams of ice we have, of water, you have to add 9.62 kilojoules of heat to make it melt. Moles, moles, grams, grams, and kilojoules. It'll tell us how many kilojoules per mole. And you end up with about 5.99. We're just going to say 6.00 kilojoules per mole. So that means this is 6.00 kilojoules. The delta H is 6.00 kilojoules. And that's true in real life. To make a mole of ice melt, which would be 18 grams of ice, you have to add 6 kilojoules of heat to make 1 mole of ice turn into water. If you had 2 moles of ice, it would take 12 kilojoules of heat. If you had 3 moles of ice, it would take 18 kilojoules of heat. That is called the heat of fusion of ice. It's called the heat of fusion of ice. It's the amount of heat it takes to make 1 mole of ice melt. That would be different for every substance. You think about making a mole of iron melt, it would take a lot more heat. The heat of vaporization is the heat required to make 1 mole of liquid evaporate. Well, the heat of vaporization for water is 40.7 kilojoules per mole. So notice it takes a lot more heat to make a mole of water evaporate than it does to make a mole of ice melt. You have to add a lot more heat to make water evaporate than to make ice melt. So that's heat of fusion is melting ice, heat of vaporization is making water turn into steam or any liquid turn into vapor. Just a couple more questions here. So this one, how much energy is absorbed when 15.5 grams of C6H6 melts at its melting point? Okay, so we're making C6H6 melt. First thing you need to know is the heat of fusion, or sometimes just symbolized H fuse for C6H6, which is called benzene. The heat of fusion for that is 9.84 kilojoules per mole. Notice the temperature is not changing here. Remember, as things change state, the temperature doesn't change until after it's changed that. And the melting point is 5 degrees Celsius for the substance. So we have 15.5 grams of C6H6. It's 78 grams per mole. And now we can use our enthalpy there. Every mole, so it's this many kilojoules per mole to make it melt. So you have to add that many kilojoules to make a mole melt. So every mole requires 9.84 kilojoules. If we were melting water, every mole requires 6 kilojoules. This substance is a little bit harder to melt, apparently. So you get an answer of 1.96 kilojoules. So to make 15.5 grams of substance melt, you'd have to add that much heat. And vice versa. If I wanted to make 15.5 grams of this go from liquid to solid to make it freeze, I would have to remove that much heat. Okay, so just the opposite can be done as well. We'll use that a little bit later when we do some changes of state. One more thing. Second rule of thermochemistry says that the delta H for reaction is equal in size, equal in magnitude, but opposite in sign for delta H for the reverse reaction. So if you look at this reaction, we have carbon monoxide reacting with oxygen from carbon dioxide. This is just the reverse of that reaction. So we have carbon dioxide breaking apart into carbon monoxide and oxygen, so it's just flipped around. So if we flip a reaction, that just changes the sign. Whereas this was an exothermic reaction, going the other way would make it endothermic. Okay, so flipping this would just flip the sign to positive. But we also have doubled the coefficients. So remember, this is kilojoules per mole of this. So if we make it per 2 moles of this, it's going to double that. So we've got to flip the sign so it's not going to be positive. It's going to be endothermic. And we would need to double this number. So it'd be 566 kilojoules. So the reaction going this way is exothermic. This way is endothermic. We have to add heat to make this break apart. Double the number